This is the last part of this topic on failure. So it's about creep. So creep is a failure in which there is a deformation in the material as a result of the consistent long-term application of the load. Okay, so this deformation takes place as a result of the load. So this deformation can be represented by this chart. Okay, in this chart you have this strain on the vertical axis and time on the horizontal axis. So when you apply a load, a stress on a specimen, and then maintain that specimen for longer period of time. Okay, that means so then there are some changes which take place into the specimen. So first, the instantaneous change is the instantaneous deformation. So this is the normal strain which we observe when we apply a load on the specimen. And when that specimen and then when that load is maintained, the stress is maintained for a long period of time, then the creep, in addition to this instantaneous creep, increases with time. And then there are then three regions of this curve. The first is the primary region, and in this primary region you can see that this is for a relatively shorter period of time. Then there is the secondary region, and here you can see that this is the longest period for the creep, and the tertiary region is also the relatively smaller region. So in this primary region, so you can see that there is a gradual increase in the strain. Okay, and the rate of strain also increases. So this increase in strain is as a result that the material is taking is providing some resistance to the applied load. So after that, there is this second region, which is called as the secondary strain, and this secondary creep. In this secondary creep, normally the region is almost linear. So it means that the increase in strain is almost linear with respect to time. So the slope in this region is called as the creep strain in this region. So this is also called as the steady state region for the strain. And in the end, when there is a strain, this in the tertiary region, the strain rate keeps on increasing and until the specimen for the creep breaks down. Okay, so and then when the breakage takes place, so this breakage is normally called as the failure is normally called as the rupture. So the increase in the strain rate in this region shows that the specimen is undergoing degradation. The intergranular bonds may be also breaking down. So this is the indication of the degradation in the material. However, from the start until the end, normally it takes very long time for this rupture to take place. So we have this primary creep, secondary creep, and the tertiary creep. The creep depends on the temperature, okay, and especially 0.4 times the melting temperature is considered as a starting limit for the temperature. That means for the temperatures above this limit, there is an appreciable increase in the creep strain. Okay, so as the temperature for the specimen increases, the creep strains also keep on increasing. Okay, so the slopes for the strain versus time keep increasing. Remember that the steady state creep is the ratio of the change in the strain with the change in the time. Okay. So the creep rate is the strain per unit of time. So therefore its units will be like per hour, per second, per year, per month, etc. Depending on how you measure the time. So, and this slide, as I have already shown to you, that it shows about the temperature, the dependence of creep on temperature. So steady state creep rate is represented by this symbol epsilon. There is a dot over here, epsilon dot s, increases with increasing temperature and the stress level. Of course, with this, if more stress is applied on the specimen, the creep strain will increase. The steady state creep can be represented by this expression as well. In this expression, both the stress and the temperature effects have been incorporated, and along with some constants. So, for example, K over here and N over here, both of these are the material constants. QC is the activation energy for the creep, so it is also a material parameter, and R is the gas constant. So this type of expression can be used for calculation of the specific creep. So steady state creep rate increases with the temperature and the sigma and the stress that we have already described in the previous slide as well. So in this slide, as you can see, that this is the slide between the stress and the steady state creep rate. Okay, it's not the strain, actually it is the creep rate, strain per unit time. So as it is shown in this chart, so you can see that for a given steady state creep rate, so you can see that a lower stress value will be needed at a higher temperature. So for example, if this much level of steady state creep rate is required, the stress level needed at 427 degrees centigrade is higher compared with the stress needed at 649 degrees centigrade. So this chart then shows the dependency of the steady state creep rate on temperature and stresses. Prediction of creep rupture lifetime. Remember that creep is a very long-term phenomena. If you want to get a complete creep curve for a specimen, normally it takes very long period of time, normally in the order of many years. However, this is not very practical, so therefore some sort of extrapolation can be found so that we can get the desired results in relatively shorter period of time. So for this, there is a equation which has been proposed by Larsen-Miller, and this equation involves the Larsen-Miller parameter m. So this equation is T, which is the temperature, times C, which is a constant normally taken as 20, plus log of the TR, which is the time to rupture. It is equal to m. So this equation says that for any combination of the rupture time and the temperature, and for a given material, this type of product will remain a constant. So that constant will be is called as the Larsen-Miller parameter. So from this constant, once that constant is chosen from the charts, then we can choose the temperature and the time to rupture from these relationships. So as an example, we can see we can have this example. So suppose we have a plot of log for logarithm of the stresses versus the Larsen-Miller parameter. So on this horizontal axis we have the Larsen-Miller parameter. On the vertical axis we have the stress in terms of the logarithms of this stresses. So as an example, we need to estimate the rupture time for an S590 iron at 800 degrees centigrade and at 20,000 pound per square inch stress. So the temperature is actually 1073 Kelvin corresponding to 800 degrees centigrade. We can apply this equation 1073 plus C, as it has been told that C is a constant which is normally taken as 20, plus log of TR. That will be equal to 24 times 10 to the power 3. This 24 times into 10 to the power 3 we can read from this chart, which should be available to us. So corresponding to 20, this Larsen-Miller parameter is 24 into 10 to the power 24,000. And then this equation can be solved for this unknown value. So in this case it is giving a value of 233 hours. So it will mean that time to rupture will be 233 hours at this temperature. And then if we want this time to rupture at a room temperature, then we can convert it using this equation here. So provided we know the activation energy for creep, etc. So this was the short description of the creep, and with that this is the end of this topic on failure, and the last two slides are about the summary of this topic. So I would recommend you to look at this summary, and later on we will do some tutorial questions.